Okay, so what we determined during that time is that sodium and potassium are really important for neuron function, also for muscle contraction. So every neuron in your body is needing to have sodium and potassium at the right levels so that they can move across the membrane and form an action potential. So back to this. Our nephrons start reclaiming good stuff by using energy to pull sodium back into the blood. And then, once sodium is back in the blood, we have negative ions follow it. So we've got all this positive charge moving up back into the blood, and that creates somewhat of a charge imbalance, and then the negative ions kind of come after it. That's an efficient system because you don't have to literally pump every single thing. You pump sodium, and all of this other stuff follows after it. So the negative ions follow it, and then also water follows it. Water follows salt. And there's more to that process than I just showed, but for this class, that's the level that we start with. So the major mover in tubular reabsorption is sodium, and then a lot of other substances follow it along with it. So we're doing active reabsorption of sodium. This spins ATP. This pulls other beneficial substances along with it. And water moves by osmosis. Water moves by osmosis. And normally, this works so well. I know this is low on the screen, but this chart is saying for water and for sodium, how much moves through your kidneys every day, 180 liters of water. And if this is working normally, you get 99% of it reabsorbed. So what you pee out is supposed to be 1% of the water in your body. Or that's not right. 1% of the water that passes through your kidneys. And then for sodium, you're filtering 630 grams of sodium through your kidneys every day and getting back normally 99.5% of it. So it seems like a lot of wasteful movement, but maybe it's wasteful to dump the whole contents of the purse instead of digging through there individually to pull out trash, but this is a system our body has. Dump out everything small, bring back the good, leave the rest in the filtrate. So that's tubular reabsorption. Okay, you might want to stand up and stretch right now before we go to the next slides.
You're saying it's boring?
No, I'm saying it's complex or mentally tiring. I don't think it's boring. But it's also Friday afternoon, and I'm a realist. All right, now we're on step 3, tubular secretion. Tubular secretion. You might put a 3 up here. And in tubular secretion, this is kind of the last chance for blood balancing. And this name to me also is not that descriptive of what's happening. So in the third step, we've got things moving from the blood into the tubules. So step 1, blood to tubules. Step 2, tubules to blood. Step 3, blood back to tubules again. Seems kind of
Say that
redundant.
again?
Yeah, step 1, blood to tubules. That's glomerular filtration. Step 2, tubules back to blood, tubular reabsorption. Step 3, blood back to tubules, tubular secretion. So we're secreting into the tubules, tubular secretion. And this is happening also using active transport. And what's mostly moving here is a pretty limited set of substances. Which I've got listed on here as drugs, ions, and protons, or acid, you can think of it. So another way that you can think of tubular secretion, this is kind of the final check on urine composition. It's the final chance to get the filtrate having exactly what we want to be in it and leave the body. Because after this, the urine we've got is the urine we've got. So after this, the filtrate is past the point of having further adjustments, mostly, and it's going to have its final composition. So in this step, we're actively transporting these substances back into the filtrate so that we can get rid of them. And one of the other major aspects of this is that it helps provide hemostasis of our pH and our ions, including calcium, potassium, sodium. We've got to have those in very defined levels. So tubular secretion is responsible for getting those final levels right. And this section, this step is happening mostly in the distal convoluted tubule, mostly in the distal. There's a video on Blackboard that I have linked to, and they are showing that this step also happens in the proximal some, which is true. But it's easier to learn it, that this happens in the distal, it happens some in the proximal. Mostly distal. So we've got, here's the blood. We just had tubular reabsorption, put back good things. But now, so like sodium came over, a lot of stuff followed it, not shown here. Now the blood can move protons, or acid, or H+, back into the tubules, and can move potassium back into the tubules, and in some cases also sodium. And at this point, the filtrate is going to head for the collecting duct. So kind of from here, the movement of most items is stopped, and from here, you can draw an arrow down, say, urine. It's tubular secretion. If we're able to get certain drugs that are small out of the blood and back into the tubules, we will. Not every drug can we do that, but some that we can. So that's your 3 steps. Remember, know their names, know their order, know where they happen. What's moving, where is it moving, and what's driving its movement. What drives this movement? What powers it? This is by blood pressure. Further down, it's active transport. So we spend ATP. Blood pressure gets the process started, but later on, it's active transport and secondarily passive transport of water. But Active transport is what I want you to know. So that's your 3 steps. You can work on memorizing those with their accompanying characteristics. So if our kidneys are working well, we need to be reabsorbing the right amount of water, which is usually most of the water. If we cannot reabsorb enough water, what does that mean for us daily? You're going to get dehydrated. You're going to be going to the bathroom all the time. You're going to become sick. You might have to keep on drinking massive amounts of water. Who's like that? What kind of people are like that? Pee too often. Have to keep drinking water. Yeah, say it loud. Diabetics. Yeah. So diabetics are not able to reabsorb enough water because they're peeing out so much sugar that the water is staying with the sugar. And if that was confusing, don't worry about it too much, but they can't pull water back in against the amount of sugar that's still in the urine. Thus, they tend to get dehydrated. Thus, they need to use the bathroom a lot. Thus, they are thirsty all the time. And that's one of the first symptoms of diabetes, is thirsty all the time. Because they're not reabsorbing enough water. They're losing too much in the urine. So to do kidney function right, most of the water needs to be reabsorbed. I don't want to go there yet. Okay. So, if we're going to reabsorb water, we need to generally reabsorb that water before the collecting duct. Before the collecting duct. And also before the distal convoluted tubule, because they're impermeable to water. What that means is that water cannot cross through them by osmosis. That's a weird situation in our body. Like most places in our body, water can always move by osmosis, and it can always follow salt or always follow solute, but this is one place where it can't. So this is, in a way, this is our body kind of like cutting it off, like, okay, by this point, the filtrate that we've got is the filtrate that we've got, and we're not going to adjust the water balance anymore. So if this needs to happen, it needs to happen before this. So let's look again at a nephron. Let's go down to this picture. So don't focus on the words of this picture yet, but on the anatomy of it. So from the beginning of the tubule system, what's this part called? Yeah, glomerular capsule, proximal convoluted tubule, the proximal convoluted tubule, which they've stretched out here, descending, ascending limb. This part is where water can really move. This part, water generally cannot move. So if water is going to move, it has to be back here before the chance is lost to move it. Okay. One exception to that. So there's an exception to that, which is this third point on here. We can make a hormone called anti-diuretic hormone, or ADH, and that makes those segments of the tubule system, DCT and collecting duct permeable. So go ahead and write that down, then we're going to write some other things over here as well. Okay, let's start with the word diuretic. Raise your hand if you've heard that word. What does it do, generally?
Stops you from peeing, or makes you pee?
It makes you
No,
pee.
One of the,
Yeah,
one
it
of
makes
the
you pee more. So we'll put that as it causes water loss. So diuretics will help you reduce edema if you have a problem with that. You don't want to use them if you don't need them, because then that will lead to dehydration and electrolyte imbalances. But diuretics cause water loss generally by increasing urination. So anti-diuretic is the opposite. Anti-diuretic hormone, ADH, causes water retention. And what would that do to urine output? Decrease. So you pee out less, you retain more. That's an anti-diuretic. And the purpose of making this is actually to keep your blood volume up and to keep blood pressure up. Did we talk about this one in ALA 2? It was just aldosterone. This ADH aldosterone stuff, I come back to it in a future lecture, but I want to introduce the terms of it here. So antidiuretic hormone causes more water retention, less urination, and it does that by letting water get reabsorbed late, so to speak, in the distal convoluted tubule and the collecting duct. And here's how it does this. This is cool. So if you have a friend that's not here today, show them this drawing later. Okay, if this is the collecting duct, I mean, they're showing this as the collecting duct. This is the state without ADH. So there's water. It can't pass through in either direction. It's impermeable. So it's like this would be insulated or fatty and water can't get through it. It's sealed, it's impermeable. ADH does something cool, which is to put these channels into the collecting duct and or the DCT. And the channels are like bursting a hole kind of through a wall. It creates a passageway for water to move in either direction. And those are called aqua, like water, porins, like a pore, aquaporins. And one place in your body where you actually sometimes use aquaporins is in the distal convoluted tubule and the collecting duct. And normally, when we're using ADH, water is going to move out of the filtrate and back into the body, and this concentrates urine. So add over here, ADH, we retain more water, we decrease urination, and that results in concentrated urine, which they're nicely showing here as, oh, it's more dark yellow now. It's being concentrated because water is being reclaimed by the body. Anti-diuretic hormone. This is kind of a review of where anti-diuretic hormone starts, where it comes from. So this is the signal that initiates us making anti-diuretic hormone. Our blood's too concentrated. We don't have enough water in the blood. We need to retain more water. That's the signal. That signals to the hypothalamus. Hypothalamus signals posterior pituitary to make ADH. It goes all through the bloodstream. The kidney is where it acts. So this is a hormone cascade for ADH. It starts in the hypothalamus. There's a releasing hormone to send to the posterior pituitary. Or no, wait. There's not a releasing hormone. Not a releasing hormone. Posterior pituitary releases ADH. It goes to the kidneys. You could write aquaporins in here. Our urine volume decreases. I think that's a good place to stop. So by this point, we've made urine. We've balanced its levels. We've hopefully retained the useful substances out of it. From that point, the urine does not change. It is what it is. But we'll be talking about what should it be, what should it have, how does it get to the bladder, how does it get out of the bladder, and then generally things that can go wrong. That will be Monday. Also on Monday, you can turn this off now.